Okay, now this is our fifth video, application of calculus to inequalities. Now, if the inequality that you are trying to prove involves logarithmic functions or trigonometric functions or exponential terms, then a calculus-based approach is often needed. So application of calculus to inequalities will be for questions where involving logarithmic functions, trigonometric functions, or exponential terms. So this is when you'll need to apply calculus to inequalities. Now, if we look at our first example, it says show that x is greater than ln of 1 plus x for all x greater than -1 and state when equality holds. Now, when you're asked to prove something like this, that x is greater than ln 1 plus x, what you're really asked to prove is that what this really represents is if you were to sketch, let's say you were to sketch y equals x and you were to sketch the function y equals ln 1 of plus x, what you're trying to show. Now, if I do a quick sketch of those, actually I can do those on Desmos for you. Just saying, if I draw the function y equals x, that's that red line there, and I draw the function y equals ln of x plus 1, and that's the blue function there, we're trying to show that x is greater than, the question says show that x is greater than or equal to ln 1 plus x. Now, we can clearly see that from the graph, that x, or the graph y equals x, is always greater than, or meaning it's above, or greater than or equal to ln x plus 1, and this is the point where it's equal to when x equals 0. That's where the two functions meet. Now, if you're trying to prove that x is greater than ln x plus 1, what we're going to do is I'll just go back to my other sheet, okay? So to prove that x is greater than or equal to ln 1 plus x, we're going to actually show, so instead of doing that, we're going to show that x minus ln 1 plus x is greater than or equal to 0. So if we let our function of x equal to x minus ln 1 plus x, we just want to show that that function is greater than or equal to 0, because see, x, and taking this over the other side, x minus ln 1 plus x is greater than or equal to 0. In other words, if this function is greater than or equal to 0, it's always above the x-axis. Now, if I go back into Desmos and draw that, so I'm going to draw x minus ln 1 plus x, okay? So again, you can see y equals x, you can see y equals ln 1 plus x. Now, if I draw y equals x minus ln 1 plus x or x plus 1, it'll be the same, okay? Then what I get is the orange function, and you can see that the orange function is always greater than or equal to 0. It always has y values greater than or equal to 0, and you can see here that we've got a minimum value of 0 when x is 0. Now, this is why we're going to use a calculus-based approach to show that this x minus ln, x plus 1, is always greater than or equal to 0. We're going to show that there is an absolute minimum at x is 0, and the minimum value is 0, so therefore this function is always greater than or equal to 0, and that's how we're going to use this method to do this proof. Okay, so I'll go back to the page and complete the proof. So coming back here, we've got function of x equals x minus ln 1 plus x, so therefore f dashed x, the first derivative, looking for stationary points, is 1 minus, now if you differentiate the log function, it's f dashed x on fx. If we differentiate that, we get 1 over 1 plus x. Now for stationary points, or for stationary points, we know that f dashed x equals 0, so therefore 1 minus 1 over 1 plus x equals 0. In other words, 1 equals 1 over 1 plus x, or 1 plus x is 1. In other words, x is 0. So therefore, we've got a stationary point when x is 0. So when x equals 0, let's just work out our y value, or our function of x, all right? So when x is 0, function of x is, putting it back up into here, into this function. Function of x is 0 minus ln 1 plus 0. So it's 0 minus, now ln 1 is 0, so it's 0 minus 0, which is 0. So also we need to look at the nature of our stationary point, okay? So let's just look at our nature of our stationary point. So we know that there's a stationary point when x is 0. So what we'll just do, instead of doing the second derivative, I'm not going to differentiate this again, okay? I'm going to look at the first derivative on either side of x equals 0. So we know we've got a stationary point at x equals 0. I'm just looking at its nature. If I just look at something like 0.1 and something a little bit below 0, like negative 0.1, I know that when x is 0, here's my f dashed x. So when x is 0, f dashed x is 0, because I get 1 minus 1 over 1. So it's 1 minus 1 is 0. Let's try when x is negative 0.1. So if I go 1 minus 1 over 1 plus negative 0.1, so that's 1 over 0.9. So it's 1 minus 1 over 0.9, and you can just do that quickly. This, we get that the gradient of the curve is negative here before 0. Then we get that the gradient of the curve is 0 when x is 0, and the gradient of the curve is positive when x is greater than 0. So therefore, we have, now because this is the only stationary point, therefore we've got an absolute minimum. So absolute minimum of, now the minimum value is 0, so this is my minimum value of x minus ln 1 plus x. So absolute minimum of 0 when x is equal to 0. So now the reason up here in the question that they're asking, show that x is greater than or equal to ln 1 plus x for all x greater than or equal to 1. If we have a look again at the quick sketch of the function, what we find is that there is an asymptote at x is negative 1, okay, and that the actual functions look like this. So we're only looking at values of x greater than negative 1 because for the function ln 1 plus x, there is an asymptote here at x is negative 1. And that's why it's asked for only values of x greater than negative 1, not for all real x, okay? As they will ask all real x in some of the other questions that we're going to do. So therefore we've got an absolute minimum of 0 when x is 0, and so therefore this function x minus ln 1 plus x, so if I look at the function x minus ln 1 plus x, I mean we know it looked like this, but it will look something like this. So this x minus ln 1 plus x, because there is only one minimum, the minimum value is 0 when x is 0, the function will look something like this. I'm not sure exactly how far these will come out or how low that is or how steep. It doesn't matter. You just know that you've got a minimum. The minimum value is 0 when x is 0. So therefore, we can now conclude that your function of x must be greater than or equal to 0 because it's always above the x-axis. In other words, its y values are always greater than 0. And so therefore, we've let function of x be x minus, see up here, we've defined function of x as x minus ln 1 plus x. So therefore, x minus ln 1 plus x is greater than or equal to 0. And so therefore, x is greater than or equal to ln 1 plus x as required for x greater than or equal to, sorry, greater than, not greater than or equal to, for x greater than negative 1. So that's our first example involving a logarithmic function. I'm going to now do another example involving a trigonometric function. Here's an inequality involving a trigonometric function. Again, we're going to use a calculus-based approach for this question. I'm going to go into Desmos again and quickly sketch this. I mean, but we could actually sketch it here ourselves. I can try a quick sketch here. And if we've got cos x, we know cos x looks something like this, okay? and we've got this 1 minus a half x squared. Now this is a concave down parabola, so we've got two functions here, y equals cos x and y equals 1 minus a half x squared. Now this concave down parabola looks fairly wide, shifted up 1 unit, so it would be a parabola like this. Now I'm not sure how wide it is, that's the thing. So what I'll do, it must actually come under here, because if it comes up over there, then it'll sometimes, oh no, it's meant to be greater then. So it must come, well, anyway, look, I'll do it quick. What I'm going to do, I'll do it in Desmos so that you can have a look, all right? Because if it actually goes under, then cos x is always, will be, oh no, cos x is meant to be greater than, sorry, it's a bit late at night here. So, yeah, cos x is this one. It has to be always above. So this other curve must be down here. But I'll go to Desmos and we'll have a look, okay? Here's, in Desmos, here's the first function, y equals cos x. That's the first one in red. Let's look at the second function, y equals 1 minus a half. So I'll just go 0.5. 1 minus 0.5 x and squared. Okay, and it is, as I've suspected, it's below, that function is definitely always below the cos x curve. Now, to be able to prove this, we're going to do the first function minus the other one, because remember, when you're trying to prove left-hand side is say greater than or equal to right-hand side, you need to do left-hand side minus right-hand side. So what we're going to be doing is cos x minus all of this 1 minus a half x squared. Now, what we've got here, we can see that that's the yellow curve, and that you can see here that this curve, cos x minus 1 minus a half x squared, is always greater than or equal to 0. Therefore, we've got a minimum there. So cos x, so this function here is always greater than or equal to 0, because its y values are always sitting above the x-axis, or we've always got positive y values. So we're going to, that's the idea of the question, same idea as the other question. We're going to use calculus again to prove this, okay? Okay, so what we're going to do, we're going to let our function of x be equal to cos of x. So to prove that, we're going to let our function of x be cos of x minus this, 1 minus a half x squared. And what we're trying to prove, we're going to prove that that is greater than or equal to 0. Okay, so this is what we're really trying to show. So we're going to show that cos of x minus 1 minus a half x squared is greater than or equal to 0. Okay, and that will show this result here. Okay, so if we let our function of x be that, let's just simplify that. In other words, our function of x is cos x minus 1 plus a half x squared. So let's differentiate that function. So f dashed x will be, if you differentiate cos, you get minus sine x. If you differentiate the minus 1, you get 0. If you differentiate this, we'll get plus a half times 2x. So we'll get minus sine x plus x, or I'll write it as x minus sine x. So that's our first derivative. Now, we may as well put this, so for stationary points, f dashed x is equal to 0. So we've got x minus sine x is equal to 0. Do this by observation. We know that when x is 0, that 0 minus sine of 0 is 0 minus 0, which happens to be 0. So therefore, we have a stationary point when x is 0. Now let's just look at our value. So also, when x is 0, let's look at our function of x. Our function of x will be cos 0 minus 1 plus a half times 0 squared. So it will be cos of 0 is 1 minus 1 plus 0, which is 0. So therefore, we have our function of x equals 0 when x is 0. So therefore, function of 0 is 0. And we know that f dashed 0 is also 0. Now we just need to show whether we have a minimum or a maximum at x is 0. Look, this looks easy enough to do a second derivative with. So instead of doing looking at f dash x on either side, I mean, we can also look at the second derivative to determine the nature of the stationary point. So the second derivative, differentiating this one more time, we get 1 minus cos x. And when x is 0, we get that our second derivative is 1 minus cos of 0, which is 1 minus 1. Sorry, our second derivative is, let's see. So this sort of isn't giving me enough information here. So I'm just going to go back here to my second derivative, and I've got the second derivative is 1 minus cos x. Now I know that my cos x function looks like that. Okay, so this is cos x, y equals cos x, and the function of 1 minus cos x will be, this goes from 1 to negative 1, it's range, this will go from 2 to 0. So therefore I can say that f double dashed x is greater than or equal to 0. Okay, so my second derivative is greater than or equal to 0. I can see this because I've sketched it. So I've sketched 1 minus cos x. So this is f double dashed x, okay, which is equal to, sorry, just running off screen. So this is my second derivative function, 1 minus cos x. I can see that it is greater than or equal to 0 for all x. So therefore my function is concave up for all x, okay? Now, for it to be concave up for all x, it means that therefore I know that I've got one stationary point, so therefore I must have a minimum. So therefore I must have a minimum at x is 0, because I know I've got a stationary point when x is 0. So therefore, if I look at my function x, which I've got up here, so my function in x is cos x minus 1 plus a half x squared. So my function, my function of x, which happens to be cos of x minus 1 plus a half x squared, must have, I don't know what it looks like, I mean we did see it before, but we know that we've got definitely a minimum at x equals 0, or a minimum value of 0 at x equals 0. So that's what our function will look like. We're not sure how wide or how steep or whatever like that, but we know that we've got, as we said, we've found one stationary point, that we've definitely got here a stationary point. So this is telling me here stationary point of 0 at x equals 0, and a minimum that the value at the stationary point is 0. But looking at the second derivative, this isn't really telling me that much. But here I can see that it's greater than or equal to 0 if I sketch the function 1 minus cos x. So therefore we must have a minimum at x is 0. The other way I can show that we've got a minimum at x is 0 would also be to come up here. I'm hoping this will work. One sec. It should. So I've got x, f dashed x. I've got, when x is 0, I know that f dashed x was 0, because 0 minus sine 0 is 0. Let's look at something like 0.1 and negative 0.1. So you can just go and put those into your calculator. If I put, instead of doing that second derivative, if I know that I've got a stationary point at x is 0. If I look at a value a little bit less than 0 and a value a little bit greater than 0, I've got negative gradient, 0 gradient here, and positive gradient. Therefore, you've definitely got a minimum. Sorry, minimum. Anyway, I know you can spell. Minimum at x is 0, and it's a minimum value of 0, because we've just worked it out here. So minimum value of 0 when x is 0. So that's another way of doing it, to show that therefore we can see that our curve is always greater than or equal to 0. So therefore we can say that cos x minus 1 plus a half x squared is greater than or equal to 0. In other words, cos x is greater than or equal to 1 minus a half x squared, as required. Okay. Examples show that x is less than or equal to e to the x minus 1. Again, you would let, basically this is what we want to show. We want to show that x minus e to the x minus 1 is greater than or equal to 0. So if we let our function of x equal x minus e to the x minus 1, looking at our first derivative, f dashed x is 1 minus, now you get e to the x minus 1 times the derivative of x minus 1, which is 1, so it's 1 minus e to the x minus 1. So again, for stationary points, f dashed x is 0, so 1 minus e to the x minus 1 is 0, or e to the x minus 1 is equal to 1. Now we know that e to the 0 is 1, so therefore x minus 1 has to be 0, so x is 1. Okay, now we can just look at the, I think it might be just easier to just look at the sign of the first derivative on either side of that stationary point. So when x is 1, your first derivative is 0. Then you can just look at a point a little bit above and a little bit below 1. Okay, you can just go to your calculator now and do that. Put the values of 0.9, so you'd get 1 minus e to the negative 0.1 here. I got roughly approximately positive 0.1, and when you put 1.1 here, 1 minus e to the 0.1 gave me a negative value. So we've got positive gradient, 0 gradient, negative gradient. Therefore, we appear to have a maximum at x is 0. Now we need to see what this maximum value is. So when x is 0, so sorry, I think I've written, oh sorry, I've just written this the wrong way around. One sec. We're trying to show, this is just written wrong. Up here, I've just taken that over there. We're trying to show that it's less than or equal to 0. Okay, so just fix that there. So we've got a maximum at x is 0. But when x is 0, let's just look at what our function of x is. So function of 0 is 0 minus e to the negative 1. So we get 0 minus, actually that's put in the wrong place. Should be doing it here. So we've actually got 1. So f dashed x, sorry, no, it's the normal function, sorry. A bit late and getting a bit tired. So when x is x is 1. There, definitely tired. So, sorry about that. When x is 1, we go into the normal function. Jeez. So, here. So when x is 1, function of x is 1 minus e to the 1 minus 1. So it's 1 minus e to the 0, which is 1. So it's 0. So therefore, we have a maximum value of 0 when x is 1. Now, if I drew that, so in other words, when x is 1, the maximum value of this curve is 0. We also have an absolute maximum value of 0 when x is 1, because there are no other stationary points that we found. So therefore, we can say that our function of x is always below, less than or equal to 0. So therefore, the function of x is less than or equal to 0. Now, our function of x is x minus e to the x minus 1 is less than or equal to 0. So therefore, x is less than or equal to e to the x minus 1 as required. And we will have, it also, they will ask you you can be asked when will equality hold, and therefore we'll have equality, you can see it here. This is x is 1 if and only if x equals 1, because when x is 1, we get that 1 is equal to basically e to the 0, e to the 1 minus 1, which is e to the 0, which is 1. So therefore we have equality if and only if x is 1. Now, for example, 4 says use ln t equals the integral from t to 1 of the function 1 on x dx for t greater than 1 to deduce that 1 minus t is less than or equal to ln t, which is less than or equal to a half bracket t minus 1 on t for t greater than or equal to 1. Now let's just look at this middle bit, that this ln t is the integral from t to 1 of 1 on x dx. Now I'm going to sketch that, okay? So we've got the hyperbola, y equals 1 on x. Okay, now we've got, remember when you integrate a function, you're looking at the area under the curve, okay? Actually, I might just draw that a little bit bigger. What I'm doing, I'm just drawing this x-axis a little bit lower, and I've got my values integrating area under the curve between t and 1. Now, this is the area under the curve, okay, this shaded bit, okay? Now, right, to find the area under the curve, it would be the integral between t and 1 of 1 on x dx, okay? But what we're going to do, we're going to break this up into 2 areas. Now, obviously, this shaded area is bigger than this rectangle that I'm drawing down here, okay? So the area of, I'm going to just label these, the sides of this. So I've got this point A, I've got B, I've got point C, point D, and point E. So I'm going to say the area of EBCD, that's that black rectangle, is less than the integral from t to 1 of 1 on x dx, which is less than, now I can do an upper rectangle or I can do a trapezium if I want, okay? I'm going to do a trapezium. Which is, now this shaded area will be less than the area of this red trapezium, which is the area of shape A, B, C, D, okay? Now, all right, let's do the area of E, B, C, D. Now, we know that the length CD, it's just a rectangle, so that area will be CD, happens to be t minus 1, and the coordinates of point B, well, this is the curve y equals 1 on x, and at the value x equals t, B, so the coordinates of B will be t, 1 on t. So this height here is 1 on t. So the area of EBCD, so if B is the point t, 1 on t, then the length BC will be 1 on t units. So this height here is 1 on t. So therefore the area of EBCD is t minus 1 times 1 on t. Now that's less than the integral between t and 1 of 1 on x dx, which is less than the area of trapezium ABCD. Now, area of a trapezium is h on 2 a plus b. So it's going to be, now h is this length here, so it's t minus 1 over 2. This length here, BC, is 1 on t, plus this length here, well, this is the curve. If we look at the length, if we look at the coordinates of point A, coordinates of point A are 1 and 1 on 1, which is 1. So therefore, the height AD, or the length AD, is just 1 unit, okay? So therefore, area of the trapezium is h on 2, which is t minus 1 on 2, BC plus AD, which is 1 on t plus 1. Okay, now expanding this, 1 on t times t is 1 minus 1 on t is less than, now this is just ln x, because we know that, or sorry, ln t. We're told that ln t is the integral from t to 1 of 1 on x dx. which is less than, now just expanding this, we get, or just simplifying it a bit, we're trying to show that it's less than, sorry, these aren't less than or equal to's, by the way, they're just less thans, all right, sorry about that. We're trying to show that it's less than half t minus 1 on t. So let's just keep the half out here and multiply t minus 1 by each of these, and we get t minus 1 over t plus t minus 1. So let's just simplify this a little bit, okay? So we get 1 minus 1 over t is less than ln t, which is less than a half. So we've got t over t minus 1 over t plus t minus 1. So I've just put each of those over t. So 1 minus 1 on t is less than ln t minus, which is less than a half. Now this is 1 minus 1 is 0, and we're just left with t minus 1 on t. And this applies for values of t greater than 1, okay? Now, when t equals 1, we will find that the inequalities or equality will hold, because when t is 1, we get 1 minus 1 is less than, now ln 1 is 0, so it'll actually equal that, which is equal to a half 1 minus 1. So when t is 1, we get that equality holds, as we can see below. So therefore we can say that 1 on t is less than or equal to ln t. Sorry, the question was less than or equal to. Just going back up here, it's less than or equal to, sorry about that. So, is less than or equal to ln t, which is less than or equal to a half, just going back up here, t minus 1 on t. Okay?